Okay, welcome back. Excuse me. What I wanted to do today is to look at basic practical skills. And and how these can be used for yourselves to your advantage. Okay. Let me just make sure I've got this in view. Okay. Okay. Basic practical skills and basic practical skills 2. Electrical installation. Now, measuring and marking out. Standards of length. Now, before anything can be measured, a standard must be fixed. The standards of length in the SI system of units is the International Prototype Meter, kept at Sèvres near Paris. Okay. Now, the standard meter is the distance between two fine lines engraved on the surface of the metal. For most engineering purposes, the meter is too large a unit, and hence it is subdivided into millimeters. 1 meter equals 1000 millimeters. Okay. Now the millimeter may be subdivided into even smaller parts, since there is sometimes a need to measure to an accuracy of much less than a millimeter. The rule. Rules used in the workshop are usually 150 millimeters or 300 millimeters long. An accurate rule must have parallel edges. Okay. Now straight, undamaged edges ends which are square with edges marks which are clear and sharp. Now care of the rule. If the rule is to last for any appreciable time, it must be looked after carefully. The following points should be observed. Now this is a rule normally referred to as a steel rule. Okay. I remember once calling it a ruler in my class, and my teacher shouted out to me, "It's not a ruler." She said it is a rule. Now that confused me a bit, because rule and a rule, because we are accustomed to having rules given to us. But I could not argue with her. She was a teacher. Okay. If the rule is to last for any appreciable time, it must be looked after carefully. The following points should be observed. Use the rule for measuring only. Do not use it as a lever, screwdriver, or scraper. Keep the rule slightly oiled to prevent it rusting. And again, as I said before, this is a steel rule. Be careful not to damage the ends of the rule. A rule with a damaged end loses much of its usefulness because it is impossible to measure a length accurately. Okay. Calipers. These are tools used for measuring objects. but with only a fair degree of accuracy. There are two chief types of calipers. Made from a grade of mild steel, they comprise two legs. They comprise two legs which are lightly riveted together at one end between two washers so as to form a pivot or hinge. The method of measuring with calipers is to span the free ends of the legs either over or inside the object to be measured. Now when the tips of the caliper legs just touch the sides of the object, the caliper is removed and placed alongside the division of a steel measuring rule. The dimensions are then read off from the rule. Okay. Now, most of you will know how to do this already, but just to make sure that for those of us who are not as clever as each other, I'm going to take this through the process. Okay. Inside caliper. These are used for measuring the internal diameters of tubular or hollow-shaped objects. The tips of the legs are spaced to the approximate dimensions of the bore, a hole drilled into an object of the bore diameter by gently tapping the legs apart. Then a trial is made by inserting the calipers inside the object. Okay. In doing this, great care must be taken that the caliper tips are inserted evenly. And that's just telling you how to adjust the caliper legs and tips. Adjust legs tips until they just touch the inner faces of the work at the widest part. Withdraw calipers, taking extreme care not to alter the position of the legs. Okay? And this is your caliper. And here is where you're taking your measurements from. That point here, okay? And this point here. So you can see how important it is not to move the caliper as a whole in order when you pull it out, okay? Okay, so that point there and that point there. That you will then set against a rule, and you can get a measurement from your rule based on the measurements you've taken using the caliper. Here, place the caliper legs tips against a steel rule and read off the measurement. Okay, and that's what we're looking at here, placing it against the steel rule and taking off the measurements at the end tips. Okay. Now, outside calipers. These are used for measuring the outside dimension of objects. Outside calipers have legs which are curved throughout their entire length. Now, to use outside calipers, the tips are spaced to the approximate dimension of the object and are then applied to fit. If they span the object too loosely, the legs are gently tapped a little closer together and again applied to the object. You would repeat this operation until you got a tight fit of the calipers to the object, and then measure it against a steel rule. Okay. Okay, again, just to give you additional information, adjust the leg tips until they just touch the outside faces of the work at the widest part. Remove calipers, taking extreme care not to alter the position of the legs. Okay, and that is our caliper. Place the caliper leg tip against a steel rule and read off the measurements. You're again doing the same similar thing here that you did earlier. Okay, just using a different caliper to achieve the same objective. Odd leg caliper. Odd leg caliper, this tool is really a special kind of compass. One leg has a curved tip and the other a sharp point at its lower end. Odd legs can be used for several different purposes, but perhaps one of their chief uses is for finding the center of any circular shaped object. So okay, I'm just trying to make sure that I've got on my camera frame. Okay. Odd leg calipers, finding the center of circular work. Reverse the curved tip leg so that it points inwards toward the pointed leg. Cover workpiece with a whitewash or mark in blue. Place the curved tip on the outer edge of the workpiece. Pivot from this position and scribe an arc. At a point on the workpiece, 180 degrees circumference from the original position, a second arc is struck. At a point on the workpiece, 90 degrees circumference from the last position, the third arc is struck, and a fourth arc is struck from a point exactly opposite that of the third position. Okay, and I think we should see that in a moment. Okay, join the point of intersection of the arcs with two straight lines. The point at which the two straight lines cross is the true center of the circular workpiece. Okay, so we're looking at trying to find the center of a given workpiece, and that is important that we find that as described. Okay, and I'm just what is it? Odd legs, and here is your odd leg caliper. Okay, making frame that in mind what we are saying. Okay, and here is what we're looking at. Okay, finding a dead center of a piece of work. Okay, tri-square. A tri-square is used for measuring and checking angles of 90 degrees. It consists of two parts, the stock or base and the blade. Good squares are made of cast steel, hardened and tempered, and are extremely accurate. There are many types and sizes in use. The most convenient size sizes for general use are 100 millimeters and 150 millimeters. The micrometer. A micrometer is an instrument from which we can read a measurement giving an exact size to 0.01 millimeter. It is an instrument of extreme accuracy and must be used with care and precision. Let me just see if I can bring this up a bit bigger. 1 second, bear with me for a second. Then bring it back to 145. Just to make sure that we can see. Okay. Okay. Yeah, hopefully we can see that without hesitation. Okay. 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 Hopefully that's it. That will do me. Okay. As I was saying, the micrometer is an instrument from which we can read a measurement given an exact size, okay, of 0.01 millimeters. Construction. The micrometer consists of a semicircular frame with cylindrical extensions, named the barrel at one end and inside at the other a hardened anvil. The bore of the barrel is threaded 0.5 millimeter pitch, and the spindle to which is attached the thimble screws through the barrel. Now the barrel is graduated in 0.5 millimeters and the rim of the thimble is divided into 50 equal divisions. The measurement is taken between the face of the anvil and the end of the spindle. The range of the micrometer is 25 millimeters, and 25 millimeters is an inch in metric terms. And here, yes, note, there are still micrometers in use, calibrated in inches, and normally read to 1/1000 of an inch. Okay. Now, sizes. Micrometers are made in various sizes. Example 0.0 to 2.25 millimeters, 25 to 50 millimeters, and 50 to 75 millimeters, and so on, up to approximately 900 millimeters. The extent of measurement is always adjustable over a range of 25 millimeters. A single micrometer with a range over 25 millimeters is available. Its adjustment range remains 25 millimeters, but it has a range of removable anvils to compensate for various lengths. These anvils are only interchangeable with their own frame and should not be used with other frames, because then you're going to get an incorrect reading based upon the frames themselves. Basically, one will not be compatible with the other. Each set of anvils and frames are numbered or lettered similarly. Reading a micrometer. Now, a micrometer is very easy to read. However, a rapid reading is only obtained through practice. The micrometer divides the millimeter into 100 parts. It measures to 0.01 of a millimeter as follows. Pitch equals 0.5 millimeter. Reads to 1/100th of a millimeter. Barrel reading in 0.5 millimeters. Thimble has 50 divisions. Division of thimble equals 1/50th times a half. 1/100 millimeter or 0.01 millimeters. Okay. Now here we have the micrometer taking measurements using a micrometer, reading in hundredths of a millimeter. Note the whole number of millimeter divisions on the sleeve, major divisions. To observe whether there is half millimeters visible, minor divisions. 3. Read the thimble for hundredths. The line on the thimble coinciding with the datum line. Okay. And here we are. Our micrometer in all its splendorous glory. Okay. Oh, sorry, okay. It's giving me a bit dark there, so let me get pulled back a bit. Okay. And here we have an example, okay. Major divisions, etc. Now you need to learn to do this for yourselves, okay? I'm not going to try to do this for you here because your interpretation and understanding and style of learning will be different to my own. And you could try to explain, I could try to explain it to you in 100 ways, but yet you will still only understand it in your own way. So try, practice, do a bit of groundwork for yourself, experiment, and find out in the use of the micrometer. To be able to read one of these micrometers is a useful knowledge to have because you can apply to any engineering role that you go into, okay, to utilize it. And here reading to 2,000 of a millimeter, 0.002 millimeters. The vernier micrometer is the same as the ordinary micrometer, but with the addition of a vernier scale on the sleeve. Read in conjunction with the thimble, okay? Now, you will come across the vernier scale in a number of things. For me, I'm just trying to, I come across the vernier scale before, but I was just trying to think where I had applied it. But it'll come to me in due course. To take a reading, note which vernier line coincides with a graduated line on the thimble. This gives the number of 2,000 of a millimeter to be added to the normal reading. Okay. Example. "10 millimeters here." Okay, you're taking your readings. Here you have 0.5. You can see that times 1 will be that. Okay, thimble divisions. Okay, you multiply 16 times 0.01 and it gives 0.16 millimeters. Okay, now remember here you have a vernier division scale. Okay, and when you times that, it simply comes up to 0.006 millimeters. Now you're going to add those together. Okay, we should give you a reading, a micrometer reading of 10.666. Now, do this for yourself so that you understand the concept and how they arrive at that answer. I could be wrong, okay, but I make no apologies for that. I'm not perfect, just handsome and good looking, okay? And this is just a guide additional showing you the relevant scale. Now I know that that bit is a bit foggy. We're not going to stress too much on that. When you look at a real micrometer, you will be able to recognize that for yourselves, okay? Now marking out. Marking out has two important purposes. It indicates whether sufficient material is available to complete the job. It serves to give an indication to the individual when the work is down to size. On rough or black surfaces where lines need to be drawn, the work should be coated with whitewash. On bright surfaces, a solution of copper sulfate or marking blue should be used. Okay? Where the copper sulfate is to be used, it is important to see that the surface is entirely free from grease or oil. Oh, crikey. Oh. Okay, sorry, it's okay, it's just my phone going off now. Okay, sorry about that. Where copy, yeah, yes, okay. Now select a datum, a line which will permit the maximum number of dimensions to be set without moving the work. In marking out, one should aim for sharp, clear lines. If a mistake is made by scribing a line in the wrong place, the work should be recoated with whitewash or engineer's blue before proceeding. Okay? You need to white out any mistakes made. If the datum faces have been prepared, then all measurements and marking out should, where possible, be taken from these. Method of marking out. As accurate fitting demands accurate marking out, the measurement used for marking out must be of a high standard. And here you have your scribes, etc., scriber, center punch, and compasses. And your steel rule. Engineer square, as we call it, okay? Three forms of measurement are possible: line measurement, end measurement, and a combination of line and end measurements. And that's something you will need to deal with for yourselves, okay, as you come to deal with those in due course. Marking out tools. Scriber, use marking lines on the surface of work, etc. Use of scriber, always work from true edge of work. Incline scriber away from straight edge, etc. Okay. And here we are looking at how the scriber should be used. Okay. Center punch. Now you all know how to use a center punch by now, so you don't need me to go through that with you at all. Use a center punch, okay? There you are. Alright, center punch to identify and punch a hole, a little mark to where you want to drill. Basically, that's its purpose, okay? Give a little tap with your hammer, and that's your roll in there. That's your mark where your drill will go, okay? Tri-square, engineer's compasses. Okay, again, this is stuff that for you to look at yourselves, okay? Don't need me to be interfering with that at all anyway. Use of engineered compasses, and here you've used them already. Basically earlier you've seen how to use these, so I don't need to spend any time on that. Okay. Working with metal, holding the work. Work can be moved in a 6-way direction as shown below. Slide in 3 directions, rotate in 3 directions. Okay, and that's what we are looking at, showing you how the workpiece can be utilized and be moved around. Okay. Movement can be restricted in a number of ways, commonly by positive location or by frictional resistance. In practice, work is held by a combination of positive location and friction devices such as vice, V-blocks and clamps and packing pieces where required. Okay. Bench and vice. Benches can be made of either wood or steel. Both are suitable materials. The two essential requirements for a good fitting bench are rigidity and suitable height. If a steel top bench is used, care should be taken when placing the tools on the bench after use. Okay, etc., etc. Okay, parallel jaw vise. With this type of vise, the jaw faces are always parallel. The body of the vise is made from iron or steel, the steel being unbreakable and more expensive. Right, to avoid damage to the surface of finished work, it is usual to employ clamps made of copper, brass, lead, fiber, or some other soft material. Okay. And here we are holding our work in hardened steel jaws serrated. Okay, holding our work in place. Okay. Workpiece must be held correctly. It should be gripped so that the edge of the material to be worked is just above the jaws of the vise, etc. Okay. Do not use the back of the vise as an anvil. It is not strong enough. Okay. Clamps. Now you know what clamps are, so here you can look at that for yourself. V-blocks and clamps. Okay. The clamp fits into grooves cut into the side of the V-block. Okay. And here we are showing you how that is done. Okay. And we have a variation on that as well. Okay. Okay. Yes. Okay. Now here we have parallel jaw vise method. Okay. Holding the workpiece in place. And here's your workpiece, parallel jaw vise on machine table. Okay. Being ready for drill. Hacksaw, you know how to use those already. Don't need me to tell you how to use a hacksaw. Okay. Okay, again, you should know how to use a hacksaw by now. Okay, thank you. Okay. Filing. Okay, filing. Okay, just here you have dead smooth cut file, second cut file, bastard cut file, rough cut file, and horse rasp file. Okay. And here are your relevant shapes of your files. Okay. Okay. Okay, I hope you found this useful. Have a good day. Bye bye for now. Thank you.